Alright, so again, we're going to skip those two chapters from week 6. Again, you can do those for extra credits. So again, skipping 16 to 17. Today we're on to 21 and 22. So,
is the homework for those chapters due next week? Or?
Yeah. Chapter 21, with the 2 being up there in Morse code. You turn the dots and dashes. Yeah, our board. All right. So 21 deals with computers. Right? After all, everybody has a computer at home and or with them in class today. Be attacked. Right?
He's probably mad because I clicked him off my camera.
Right? So computers. Right?
No, I clicked him that way.
So computers have changed quite a bit. After all, the first computers used to be on the order of the size of this room or larger. Were made using vacuum tubes. Right? Took huge amount of power in order to run them. And then usually they didn't work. Okay. So mainly in terms of turning these things on, they would usually have to wait till nighttime when the rest of the city was dark. That way they could then flip the switch on the computer because it took that much energy to run it. And then, of course, after they turn it on, then the vacuum tubes would blow up. And it would be down really right after they turned it on. Okay. And we know in terms of debugging a program, what that comes from. Yeah. Yeah, it comes from actually getting the moth out of the actual computer. So when they talked about debugging a program back then, they actually meant it. Right? But now you think of, the computers now, after all, turning people with their laptops in front of them, far more powerful than what they had back then. Okay? More powerful than what they used in order to put man on the moon. Okay? In terms of your car has a better computer than what they used for the moonshot. Right? So computers keep on changing. So you think about whatever the programs here. Really you guys end up updating because of the programs you run. In terms of software, keep on demanding more and more and more space. So you have to buy a new computer in order to run the programs you want to run. Right? Oh. So in terms of that, after all, when I started college and took some programming courses, we used to do our work on using punch cards. Right? You typed it up. You got those punch cards, which you then had to make sure it didn't get creased or folded or bent. Okay? And then make sure the cards always stayed in the right order, otherwise you programmed them right. Yes?
What about the old phone system? Were they patch the phones?
Yep, just patch them in. And you used to have party line, and you would be on a line with 3 or 4 other houses. Yep. Okay? So yeah, so you think in terms of our technology, after all, payphones now basically are a thing of the past. They are very few and far between because now everybody's got a cell phone. There's no need to have payphones anymore. Right? They've gone away. After all, the one that used to be over here in the stairwell is gone. Everybody has their own phone. Right? So in terms of computers and where they're headed, so you got in terms of the next advances in computers. So at some point in time, your computer could be part organic. So your computer could have DNA in it. Now, you think about what DNA actually is. DNA is merely just a storage material. All it does is it holds the code for you.
You mean like our DNA?
Yeah.
You mean like it could be fused with us? Like a chip inside of us?
No, be merely in the computer.
Hmm.
You could use DNA merely as a storage material for programs. Because merely that's all it does in you, it just holds the code. That code produces you. You also have in terms of quantum computers, which they're working on. Okay. Making use of quantum mechanics and spin states. So there's a number of universities working on putting these things together. There's been a few papers out about the different places saying that yes, they succeeded in putting together a quantum computer.
What kind of operations does that computer do? Is it just for like calculating, or is it like a really good computer just for everyday purposes?
Right now it's just for, trying to get it to do calculations. Okay? And so, right now you think about your computer, it's based on binary, right? Ones and zeros. Yes and no's. Okay? Quantum computer, you would have more possibilities than just 1 and 0. Because it's all based on the spin state of the electron. So maybe you could have a yes and no and a maybe. Okay? In terms of possibilities. And there's been some, weird papers out about quantum computers. There was one paper that said that in a quantum computer you wouldn't even have to turn it on because the answer is already in there. Okay? So, yeah. So in terms of your computer, as we said, you think in terms of binary. Right? Okay. And if you think about our number system is decimal or base 10 for our system. Right? So in our system, in terms of the place values, you have the ones, tens, hundreds, thousands, 10,000, so on, right? So in our system, we have in terms of 10 to the first, 10 to the 0, 10 squared, 10 to the third, right? So this would be the ones, tens, hundreds, thousands, 10,000. Okay? And in our system, we use, to represent the numbers, the digits, from 0 through 9. Okay? In binary, same type of deal, except for now we have 2 to the 0, 2 to the first, to the second, to the third, to the fourth, and so on. So now we have in terms of the 1s, the 2s, 4s, 8s, 16s, 32s, so on and so on and so on. And in binary, we use the digits 0 and 1. Right? So think in terms of octal, which is base 8. It would be based on powers of 8. And it would use the digits 0 through 7. And then if you went to hexadecimal, which is base 16, in terms of representing those, you use the digits 0 through 9, and then the letters A through F. So then, for example, given a number in binary, so given something like this, And I want to know what is that in base 10. Right? Well, in terms of place values then, if I work my way across, you got that this is the 1s, this is the 2s, 4s, 8s, 16s, 32s, 64s, 128s, and then 256s, right? That's okay. Going up by 2s. 2, 4, 8, 16, 32, 64, 1, right? So on and so on. So now if I want to know what is this number in base 10, well, we have 1, 256. We have 1, 128. No 64s. We have a 32. We have a 16. We have an 8. No 4s. 1, 2. 1, 1. Okay. And so the next step then would be to add that all up. And we get whatever this number is in base 10. What?
Oh, he's going to do it.
He's going to do it, all right.
He's going to do it.
How much?
30.
How much?
443.
443? Right. Everybody got 443? Okay. Right. So, given a number in binary, being able to convert it into the corresponding base 10, right? Which means then, of course, the next question will be is, given a number in base 10, can you convert it into binary? And, yes?
So, so that would that be 10 to the 400?
No, it would be just 443.
It's the sum of all the rest of the numbers, right?
Right. This number in base 10 would be 443. Okay? Okay? Right. So now let's take 443 and go the other way, because we know what the answer should be. Right. I'm going to convert that number into the corresponding binary. So in order to do this, all you have to do, be able to do, is to divide by 2s. And realize that every time that the number is odd, the remainder will be 1. Every time the number is even, the remainder will be 0. So we divide by 2s. So I divide 2 into 443. This is going to be 2, this is going to be 2, this is going to be 1. The remainder will be 1. Right? Right? Right. And we just keep on going. So we divide 2 into this. This will be 1, 1, 0. Remainder is 1. Okay. Now we divide 2 into 110. So we divide 2 into this. And this will go 55 times with the remainder of 0. Divide 2 into 55. So 2 goes into 55 how many times? How much? 27. With a remainder of 1. 2 goes into 27. 13 with the remainder of 1. 2 goes into 13. 6 times, remainder of 1. 2 goes into 6, 3 times, remainder of 0. And then 2 goes into 3 1 time, a remainder of 1. And that's where we stop. So once we get a 1 at the bottom, we're done. And now I want to write out the number. And so to write it out, we actually write it out in reverse order. So it's going to be 1 1 0 1 2 3, and then 0 1 1. And that would be our number in binary. Huh? 443 in binary will be that number, okay? Well, everything is represented in binary, so in terms of all the letters on your keyboard, I'll have a corresponding binary notation to it. So then, for example, everybody take a moment. And what would that number be in base 10? What?
71.
Yes.
I didn't even need a calculator.
It's twos, powers of twos, not that hard. 1s, 2s, 4s, 8s, 16, 32s, 64s, 128s, 256, 512, 1024, 2048, 4196, so on. Just double. Right? Right? So we do this one, you should end up at
127.
no. What was your answer?
60.
I got 71.
I got 71 too. What? Should be at 71. Okay? After all, again, it's the 1s, 2s, 4s, 8s, 16, 32s, 64s.
And you add those all together.
Well, you have a 64, you have a 4, a 2, and a 1. You don't add these in because you don't have any of those.
But
But
didn't we add in the zeros?
no,
What?
no, we did not add in the zeros.
I just blew
Holy shit.
You don't add in the zeros because they don't have any of those.
So no matter how long the code is, you always start at the end and work your way back, doubling. Or
Yeah, but anyway. Right? So you should end up that number in binary. From binary to decimal, this number will become that. Right?
and you said you always.
Well, yeah, it always starts here, right? Even in our number system, we go 1s, 10s, 100s, so on, right? Same thing here. 1s, 2s, 4s, 8s, 16, 32s, 64s, so on, right? Okay.
Reverting that back seems kind of hard though.
Kind of. Well, that's my next question, and let's come up with another number. And now we want to convert the other way. So, given this number,
It sounds tedious. So like you do like a 20 number thing, and someone's like, okay, what's this? And another number, and you have to start all over.
Well, because there's 164, 1, 4, 1, 2, 1, 4.
Add those two.
So you have
right? So, what is 375 in binary? Shouldn't start out with a 0. Because a binary number will start with, it will start with a 1. Okay? You don't need a 0. There's no need for a 0. Just like if I tell you to write out the number 212, you don't write 0212.
Is it 1011101?
You got an app on the phone, huh?
Yes.
There's always an app for everything, right? There's an app for that. Right? And then depending on some calculators, you look on your calculator in the owner's manual, you may find that your calculator will automatically also be able to change a number into binary, providing you actually know how to use the toy. That's the other thing, right?
Yeah, that's scientific.
Yeah. So yeah, a lot of those will automatically change it.
Or did he give 11101110?
What did your app get you, Casey?
1011110.
Is that?
That's what you said, but that's what you just said.
All right, so let's do it. All right. So again, we said to change from base 10 to binary, we divide by 2s, okay, which is not that hard. And the other thing to remember is every time that the number is odd, the remainder is 1. Every time that it's even, the remainder is 0. Right? So we just work our way through. We divide 2 into this. So this is going to be 1, this is going to be 8, this is going to be 7, that's going to be a remainder of 1. Divide 2 into this. This will be 93 with a remainder of 1. Divide 2 into 93. We get that this will be 46, remainder of 1. So, continuing on, 2 goes into 46. 23 with a 0. 2 goes into 23. 11. Remainder of 1. 2 goes into 11 5 times. Remainder of 1. 2 goes into 5. Remainder of 1. And then 2 goes into 2. And we get that, right? And then to write it out, start at the bottom. So we get 1, maybe, 1, 0.
Yeah,
Maybe
yeah,
0.
I wrote it from the top, so did
And then we get 3 1s. And then we get a 0, maybe. Or maybe not. Slowly getting there. 0, okay. And then we have 1, 2, 3 1s. All right.
Go back up just a little bit.
Yeah.
Wait, but I thought your first decimal was
Right?
Oh, I see what I went wrong.
Okay? So again, when you write it out, you want to start down here, that goes here, and then work your way back up your chart. Right?
I guess
I got it.
Got it? Alright. So that's what you end up with. Hopefully you don't have a bunch of dots on your paper like I have up on the board.
So your last remainder is always going to be the second binary decimal, because you're always going to start with just like what you come to at the bottom. Of your
Right. It's always, the binary number is always going to start with a 1.
Okay.
Okay? You're not going to start a binary number with a 0. Because there would be no reason to have that 0 in that spot. Okay? All right? Or you do like Casey and you find out that yes, there is an app for that.
Just cheat. You don't like that.
Problem solved.
Right? There's an app for everything. Okay?
Real world application.
All right. Okay. All right. What about decimal numbers? You actually have, I think, one of the homework questions deal with a decimal converting, right? So he said, going across to the, in terms of whole numbers, it went 2 to the 0, 2 to the first, 2 to the second, and so on, right? So now if you think in terms of decimal numbers, right? Well, if you think about our system, it goes 10 to the first, to the minus 1, 10 to the minus 2, 10 to the minus 3, 10 to the minus 4, and so on, right? Tenths, hundredths, thousands, 10,000s in our system, right? Well, same thing in binary in terms of the progression. It's going to be 2 to the minus 1. So 2 to the minus 1, 2 to the minus 2, 2 to the minus 3. Right? So 1/2, 1/4, 1/8, 1/16, 1/32. So. Point, yes.
How is that any different from what we were just writing? Like we wrote that a couple minutes ago. You know what I mean?
Well, now we're talking about dealing with numbers that are less than 1.
So it's backwards?
Yeah. So, again, the progression works the same as in our system. We do tenths, hundredths, thousands. In binaries, it would be in terms of the 1/2, 1/4, 1/8, 1/16. So, right? So, in terms of your computer,
No man's land. What does that even mean? What it means is any place too intimidating. It's any place that says no. You can't. So yeah, you can call that no man's land if you want to. But some of us, we just call it home.
and the commercial.
If you're the kind of person who's always wondered what's inside a computer, then this is the video for you. What we're going to do here is open up a machine and look at the 7 major components that you find inside. The motherboard is the heart of the computer. Every part either sits on the motherboard or connects to it in some way. In this machine, this big red rectangle is the motherboard. The CPU is the central processing unit. It's the brain of the computer. It runs the software and processes the data that you're working on. In this machine, like most, the CPU sits under a big heatsink and fan, as you see here. The people who design CPU chips often leave behind pictures or sayings on the surface of the chip. They're incredibly tiny. You have to use a microscope to see them. But like the Easter eggs in a video game, they're there to amuse and surprise other people. The RAM is the random access memory, and it sits right on the motherboard. It holds the data and the software that you're currently running. On most motherboards, you'll find 1, 2, or 4 banks of RAM. Adding RAM to your machine is a really simple way to speed it up. This is what a stick of memory looks like. To add it to your machine, just find an open slot on your motherboard and slide it right in. This is the video card, and it connects to the motherboard with a special video card slot. The video card creates the images that appear on your monitor. Most motherboards accept either an AGP or a PCI Express video card. Serious gamers will upgrade their video cards every 3 to 6 months to get the best performance. The latest thing is to have 2 or even 4 video cards in a single machine. The power supply usually sits at the top of the case, and surprisingly, it supplies the power that the computer needs. All these different wires that you see in the case are coming from the power supply. A high-end machine can burn up to 800 watts. If you left that machine on 24 hours a day for a year, it might cost $700 just to run it. That's as much as some people spend on a whole machine. This is the hard disk. It holds your information even when the power's off. When you turn the power on, your software and data loads from the hard disk into the RAM. If you've got an old machine that you're ready to donate or recycle, it contains a lot of personal information. Deleting the files is not enough because someone with the right software can undelete those files. If you want to truly erase your data, you've got to destroy the drive. This is the optical drive. It sits in the front bay of your computer, and it uses a laser to read or write CDs and DVDs. CDs and DVDs can take an incredible amount of abuse. The one thing they can't handle is deep scratches. To protect your data, always keep them in a sleeve or a case. So there you have it. Those are the 7 major components that you'll find in any normal PC.
Yeah. But again, family insurance of a computer and how it works, right? Let's see. And with that, let's give you a few minutes to get together with your group and pull together your thoughts on the day, and we will do the presentation.